There we go. All right, so polar coordinates. Now, today is the day where we actually get to talk about polar coordinates. I'm saying this because remember, in previous classes we saw some little bit, just a little bit about polar coordinates. What? Well, we saw what are radians and how do you use radians and how you convert from radians to degrees and from degrees to radians, right? Remember these guys? We saw this. This is just a little bit that we saw from radians, from polar coordinates. But today we are actually going to talk about what are polar coordinates. For that, let's begin by understanding that there are some quadrants in the plane. Quadrants, what is that? Well, that is the name that each and every one of these corners take, right? So for example, this corner over here, the one where the x is positive and the y is also positive, this corner over here is called the quadrant 1, right? Quadrant 2 is going to be this corner over here, the corner of the top left. This is going to be the corner number 2. In this one, the x is negative. Look, these ones are negative. And the y is positive. This is quadrant 2. Quadrant 3, sorry, is right underneath that. Right under that one. Is the one where the x and the y's are both both negatives. This one is the quadrant 3. And quadrant 4, the one that is missing. Positive in x's, negatives in y. Quick way to remember is just count them from right to left. 1, 2, 3, 4. There we go. In the opposite way of the clock. 1, 2, 3, 4. That's it. Now, those are the names that we give to quadrants simply because we need to say in what quadrant a point is located. So for example, point P, this one over here, P, with coordinates 3, 5, this point, 3, 5, is located in quadrant 1, right? And that is important. That is important. Now, quick thing to know. If a point is on one of the axes, so for example, this one, 0, 10, this, a point right on the y-axis, that point is not on any of the quadrants, right? It's not in quadrant 1, it's not in quadrant 2. It is exactly on the axis. So that point doesn't belong to a quadrant, all right? The only points that belong to quadrants are the points that are actually in the corners, not in the axis themselves. All right, let's continue. Let's jump into a little bit of an introduction about polar coordinates. All right. So let's say we have a point A. We have a point A on the plane, this point. Now, it is very, very easy to know the coordinates of this point A. We have been studying these coordinates from 6th grade, right? The coordinates on this point we know are going to be 4 and 2. 4 for x and 2 for y, right? We know those are the coordinates. All we have to do is just count, right? 4, 2. 4, we go from 0, 0 to the point. That's going to be 1, 2, 3, and 4. That means in x we have 4 units. And then we go up 2 more units, right? Because that is the point. We go up 2. 1 and 2. So we have 4, 2. Beautiful. X, y. Every single coordinate that we have seen so far is in that order. X, y. Always first x, second y. That's it, guys. So far, so good, right? These are the usual coordinates we use in math. These are the usual. We haven't seen anything different than these. These are called rectangular coordinates. Go ahead and write this down somewhere. Rectangular coordinates. Why? Simple, because if we were to count it, look at this. The point kind of makes a rectangle, right? With the coordinates. It kind of makes a rectangle. So this is exactly why we call them rectangular coordinates. We can say this rectangle has a width of 4 and a length of 2. So we can kinda describe a rectangle here. Kinda. This is why we call them rectangular coordinates. All right. These are not the only coordinates we have. Today, we're going to learn a new type of coordinates, polar coordinates. Take a look at these. We can use the distance from the origin to the point. What? Origin? Distance? What is that? All right, the origin, in case you didn't know, the origin is the point 0, 0, the center of the Cartesian plane. Here, this point over here, right? And our point, the one that we want to calculate the coordinates, is this one, the point A. So I am saying exactly this line from 0, 0 to A. This is going to be the letter R. The distance from the center, in this case, my line is a little moved to the left, but it should be exactly in the center, right? So from the center to the point A, that is a distance, right? We can measure that. We can take a ruler and measure that if we want to. Now, of course, in mathematics, we most of the times don't use rulers. We use formulas and calculations. So these can be found with some formulas as well, right? That is the measure R. But also the angle of elevation theta. What do you mean by that, teacher? This little angle we make from the line X all the way to our line R. This is going to be theta. Again, the angle of elevation is this one. This is going to be our angle of elevation. So with these two pieces of information, we can create a new set of polar coordinates for the same number. Remember, the number before, the coordinates of the number were 4, 2. But now those coordinates can change and still represent the same number. These are called polar coordinates. Beautiful. In our case, these are the coordinates for our point. Look, we have an angle of elevation of theta equal 26.57. This is the angle of elevation. I did this with some mathematical software that gave me that this is the angle of elevation. And my distance from 0, 0, from the origin to the point, is going to be the letter R. This distance is 4.47. So we know distance 4.47, angle of elevation 26.54, meaning that we have our new set of coordinates. 4.47, 26.57 degrees. These are the new sets of polar coordinates, R, theta. All right, guys? And we can represent every single number, every single point in the Cartesian plane. We can represent them with polar coordinates as well. All right. We can take a look at a video to kind of expand this. Let's see if it works. If you guys cannot listen to the video, just let me know, all right? Let's see what we can do here. Let's increase this to the maximum and this again to the maximum. And I'm gonna give it subtitles. All right. Here we go, guys. Please, you need to listen to this, all right? So please increase the volume of your computer or of your cell phone. Increase it as much as you can, all right? Here we go.
This video is meant to be an introduction to polar coordinates. First, let's review standard Cartesian coordinates. You've probably worked with these quite a bit. When you write down the coordinates of a point as x, y, the first coordinate is telling you the horizontal displacement from the origin, and the second coordinate is telling you the vertical displacement. So for example, the point 3, 2 is where you would arrive if you started at the origin, moved to the right 3 units, and then moved up 2 units.
So far, so good, right? Right, guys? Please tell me in the chat or something. Are you guys listening to this? Are you guys following the instructions here?
Yes. Yes, we listen.
Beautiful, beautiful. Thank you, guys. So far, so good, right? Let's continue.
Similarly, negative 2, 4 is where you arrive when you go 2 steps to the left, 4 steps up from the origin, and 1, negative 3, 1 step to the right, and 3 steps down. Using Cartesian coordinates is very easy to describe vertical and horizontal lines. They're simply the set of points for which one of the coordinates is constant. But you could imagine using different information to describe where you are in the plane. So we could let r stand for the radial distance from the origin, and we could let theta represent a direction as measured from the positive x-axis moving counterclockwise, and we're going to measure in radians.
All right, now that part is extremely important. In this video, the guy is measuring theta in radians, right? But what are radians? Okay, we know that, right? The last class, we talked about radians and we change degrees to radians and radians to degrees. Radians is just another measurement for angles, all right? Remember, when there are no units, the units are radians. So here we have pi over 12, pi over 6, and pi over 4, pi over 3. We have a lot of radians in here, right? Let's continue.
Now we'll notice that the positive x-axis could be described either as theta equals 0 or as theta equals 2 pi. So there's a redundancy here, but actually there's a redundancy everywhere. The coordinates theta and theta plus k2 pi represent the same direction for all integer values of k.
All right, what the guy is saying here is that this, at 0 degrees or 0 radians, it's also 2 pi. Now, if we change 2 pi to degrees, this is going to be 360. So what is happening here? Is that this, an angle of elevation of 0 degrees, is the same as going around an entire circle, 360 degrees. That is what happened. That is what's happening here, going around 360 degrees. So 0 is the same as 360 degrees for our plane, for our polar coordinates. Now, that redundancy happens everywhere. Because if I go up 90 degrees here, pi over 2. This is 90 degrees, right? Pi over 2. Now, you can do these calculations by yourself. You can do pi divided 2 multiplied by 180 divided by pi. That was the formula, right? So you can do these calculations and change pi divided by 2 into degrees. You will have 90 degrees. This is an elevation of 90 degrees. But that could also be from 90. I could take another round, right? Another circle and reach the exact same point. So from 90 degrees, I could add 360, an entire circle. So the angle theta is now theta plus 360, and it is the exact same number. So this redundancy of one angle being 2 happens everywhere. All I have to do is just add 360. In other words, 2 pi 360. But I don't have to just add 2 pi. I don't have to just add 360, 2 pi. I could take one circle and then another circle. Instead of adding 360, I could add 720 degrees. 2 circles. This is exactly why this k is here, because this k means the amount of rounds you are going to add to the angle. This is a way we have to express an angle in a lot of different ways. All right, let's continue with this.
Let's look at an example. Where is 4 comma pi over 3? So the radial distance from the origin is 4, and our direction is going to be pi over 3 measured from the positive x-axis.
Now, of course, if you're having difficulties with the radians, if you don't really know how to measure radians, you can just change pi over 3. You can just change it into degrees, right? And we can measure degrees, right? Pretty simple. So that is one way. Or if you have these radial, these angles like this, located like that, pi over 3, pi over 4, and so on and so forth. If you have that, then you can just take a look at where pi over 3 is going to be, right?
That means this is the point we're describing. But as we saw, polar coordinates are not unique. So let's explore this example some more. Here's how we originally thought of this point. Pi over 3 radians from the positive x-axis measured counterclockwise, and then 4 units away from the origin.
By the way, you always measure these angles going up. That is called counterclockwise, right? You measure the angle going up, counterclockwise. What do you mean by counterclockwise or clockwise? All right, if you happen to have a watch with you, or any type of you need a watch that have the little hands, right? A digital watch doesn't work. The one from your cell phone doesn't work. If you remember how those watches work, you know that the little hands move downwards, right? To tell the time, the little hands move downwards. That is called clockwise because they move in the direction of the clock. Clockwise. So counterclockwise means in the opposite direction, then going up. We measure angles counterclockwise, so in the opposite direction of the clock, going up always, all right?
We could add 2 pi to the direction coordinate, and that means we'd circle around and then arrive at this direction, and then, of course, move 4 units out. So 4, 7 pi over 3 are also polar coordinates of the same point.
Did you see that? Did you see that? Did you see that? The guy just explained my example. All right, we have a same r. Remember, r, the first number in the coordinate, r, is going to be the measure from the center to the point. So we have 4. For what? 4 centimeters, 4 meters, whatever the units are. 4. But the angle was pi over 3. Pi over 3. This is exactly 60 degrees. The angle was 60 degrees. But if we go around and then reach the exact same line, again, by doing 360 degrees, then the angle changed. This is no longer 60. This is 60 plus 360. This is 420. We just did 420 to reach this point. A little bit and then a whole circle. And this happens for every single point. These 2 coordinates represent the exact same point in the plane.
But we could also subtract 2 pi from the direction coordinate and obtain negative 5 pi over 3. So in this case, we would travel 5 pi over 3 units clockwise from the positive x-axis and moving 4 units out once again, arrive at the same point.
Did you see that? Now we can actually use negative coordinates. Not all of the coordinates have to be positive. We can measure, if we have this angle as negative, then that means we are going to measure it clockwise. Going down. How beautiful is that? This is exactly 300 degrees. If we go down 300 degrees, we are going to reach the same line. Of course, the number 4 hasn't changed because the measurement from the zero, from the origin to the point is exactly 4. As always, we haven't changed that, but we have changed the direction of the angle. Look at that. So we can go up and then make as many circles as we want, and we have some angles. But we can go down and do as many circles as we want, down, negatively. So we have a lot of possibilities here.
Here's a sneaky possibility. We could add pi to the coordinate pi over 3. And by doing so, we're sort of pointing in the opposite direction, which might seem like a problem, except if we back up by taking r to be -4, we once again arrive at the same position.
Did you see that? Okay, now we have the possibility of r, the measure r, the first number, being negative. How? All you have to do is, instead of go on the direction of the angle, measure it backwards. Since the direction was like this, you were supposed to measure the 4 in this little line. 4 would be here. 1, 2, 3, 4. This would be the point, 4. But we're doing -4. So instead of doing it in this direction, we're going to measure it in the opposite. This one. 1, 2, 3, and 4. Our same point, but now with a different number in the R. Of course, that means I have to change the theta as well. Instead of 60 degrees, I have now 60 degrees plus half a circle. 60 plus 180. This is now 240 degrees. All right, let's continue with this.
So here's a pretty non-standard way to do it. Usually, when you're describing points in the plane using polar coordinates, you try to use a positive value of r, but it's important to interpret what happens when r is negative, because you will often have to do so when you're dealing with polar equations. So this is yet another way to describe the very same point in the plane. Polar coordinates are non-unique. There are infinitely many ways to describe the same point.
All right, now let's stop the video right here because we're gonna jump into some conversion formulas, and I don't want to do that at least today. All right, let's continue with our explanation. Where is it? Here it goes. All right, let's study how do we plot points using polar coordinates. How do we do that? So the best way for me to explain this is with an example. Here's the first one. Let's try to plot this point. Now, as you can see, we have one coordinate, 3, comma, and then a second coordinate, but this coordinate has a pi. So we know this is an angle. And since this angle doesn't have degrees or something like that, since this angle doesn't have a unit, we know this angle is in radians, right? So we want to plot this polar coordinate in the plane. Where do we put it in the plane? That is the question. Where do we put it in the plane? All right, the first thing we have to do is remember that plotting radians can be kind of hard. So one way is to change that angle in radians to degrees. That is one way. Change it from radians to degrees. We're going to change it. And to do that, we're going to use our formula. We saw this formula in the previous class. Instead of rad, we're going to write the angle in radians. Put it in the calculator and see what is the answer. All right. In the chat, David Leonardo says, Profe, ya llegué, tenía problemas con el internet. All right, David, don't worry, brother. It's okay. You're here, so that is what counts. Welcome. All right, let's continue. So let's try to change these radians into degrees. Just put it in the calculator, and we get that the answer will be 300 degrees. Look, the little circle represents degrees. So we have 300 degrees right there. Beautiful. Now what do we do? Okay, now that we have 300 as degrees, now we know that we can plot this in the plane a lot easier, right? We know the point 3,5 pi over 3 is the same as 3,300 degrees. Now, if we like to plot using radians, we can plot this one. It is okay. But to be honest, I don't even know how to plot using radians. But degrees, okay, I know how to plot degrees. Degrees are pretty easy, to be honest. We even have a piece of material that measure degrees, right? A protractor. We have that one. So we can use the protractor to plot points, right? But we don't have a protractor that measure radians. We don't have that one. All right, so from here, this will be the point here. That will be the location of the point. To plot this point, you will need two things. Number one, a protractor that lets you locate 300 degrees. And then a ruler that lets you measure 3 centimeters in this case. All right? That is the process. Measure the angle and then measure the units. That's it. That will be the location of our point, 300 degrees. Same as 3,5 pi over 3. That is it. Let's do a different example now. How about this one? What happens if the angle is negative? 2, negative pi over 4. We're going to do the exact same process. Now, plotting radians is kind of hard. So let's just change it into degrees. Negative 5 over 4. If we put it in the calculator with the formula we have, this is negative 45 degrees. So now we know we can plot 2, negative 45 degrees. How do we plot that? Just like this. But remember, since the negative is in the degrees, now we don't calculate 45 degrees up. No. It is negative. So we measure it downwards. 45 degrees down, and then using a ruler, we measure 2 centimeters. There you go. 2 centimeters will be exactly right there. This is the point. 2, negative 45 degrees. That's it. That is it. Another example. What if we have something like this? 3,0. 3,0. All right, so 0 is in radians. So of course we can just do the exact same formula to change the radians to degrees, but we don't have to. An angle of elevation of 0 radians is 0 degrees. We haven't elevated the point. The point is exactly on the x-axis because it has 0 elevation. 0. That is the degrees, 0. But the R is 3. R is the measurement from this origin, right? So we count 1, 2, and 3. There we go. There will be the point. That is 3,0. 3,0. All right? It is that easy, guys. It is that easy. But in this case, we do need a couple of tools. We do need a protractor or something that lets us measure angles, and we need a ruler. Beautiful. Finding points using polar coordinates. All right, let's do this one. Let's do the last one. Negative 2, pi over 4. In this case, the R is negative now. So the measurement from 0 to the point, from the origin to the point, is negative. So how do we do this one? The same process, guys. We don't know how to we don't know how to measure radians, so we change the radians to degrees. We use the little formula. Instead of rad, write down the pi over 4. Put it in the calculator, and we have that the degrees are 45 degrees. So instead of doing negative 2, pi over 4, we're going to do negative 2, 45 degrees. Now, this one is a lot easier, right? In the plane, we go up 45. The degrees are positive, so we go up 45 degrees, right in the middle, 45, right? And now the measurement is 2, right? The unit from 0, from the origin to the point, is negative 2. So we don't count 2 up. The point should be here, but it is not. Why? Because it is not positive. We are not going to count it on the what should be the line. No. We are going to count these 2 downwards, negatively, in the opposite direction. Remember, 45 degrees would make it so that this will be the direction, the little dotted line. but we are doing -2, so we measure it backwards. Right here would be the point D, right here, with a measurement of -2. This would be the point now, -2,45. That's it, guys. That is how you measure, how you plot points in the plane using these coordinates as well. Now, the easiest way for you to get better at this is to practice. So we're gonna begin with these exercises. Please, guys, for the rest of the class, work on the exercises 9 to 38 of the page 725. I'm gonna stop the recording here, and remember, if you have any questions, I am here for you guys.